Okay, so now you must be thinking that why we care about basic solution. So don't worry, let's continue. First, among all the basic solutions, we see that some are feasible and some are infeasible. The reason is that when we are defining basic solutions, we are only talking about those equality constraints and we ignore the non-negativity constraints. So if we want to check which basic solution is feasible, then we only need to check whether all its variables are non-negative. Okay, in that case, we say it's a basic feasible solution, or abbreviated as BFS. So, for example, here, if we have all those basic solutions, then checking whether they are feasible is very easy. If you have a computer, if you can write loops and if, then rah 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 rah, immediately you see here you have two negative numbers. So the third and the fourth basic solutions are infeasible, and we have four basic feasible solutions here. Okay, that just that simple. So why basic feasible solutions are important? Because they are just extreme points. Okay, this is very important. For a standard form linear programs, those extreme points are exactly those basic feasible solutions. And this immediately implies the following. Suppose we have a standard form linear program. If there is any optimal solution, then there must be a basic feasible solution that is optimal. So, looking at these two theorems, you immediately understand the value and benefit of looking at standard form linear programs. In general, we want to focus on extreme points, okay? Because we know extreme points or those corner points are candidates of optimal solutions. But with a graph, it's easy to get those extreme points. But if you have thousands of variables and thousands of constraints, it could be hard. But here, basic solutions and the basic feasible solutions, their definitions are purely algebraic, only with numbers and equations. So with a computer, it's very easy to enumerate all those basic solutions and the basic feasible solutions as long as you don't care about time complexity. Okay, so for these kinds of special types of linear programs, extreme points are so special that they are just basic feasible solutions defined in the previous way. So all we need to do is to focus on basic feasible solutions. That's very good. So even though we cannot prove that theorem 1 because it requires a much more advanced course, but to get an intuition is very easy. We know that this is the feasible region of our original linear program with two inequality constraints. So after we put them into equality, we get four variables. Two are original variables, x1 and x2, and two are static variables, x3 and x4. So that's why we have six bases and four basic feasible solutions. And then you immediately see that, okay, there are four basic feasible solutions. And if we only look at their basic part, we have 2, 2, 3, 0, 0, 3, and 0, 0. And indeed, they correspond to these four corner points. Okay? And this just gives you a basic intuition that those algebraically defined basic feasible solutions, like here, exactly corresponds one-to-one to those corner points or extreme points of a feasible region. Obviously, this kind of graph and intuition is rough, so it's just giving you an idea. We are not really proving theorem 1, but hopefully you are convinced that basic feasible solutions indeed are extreme points. Okay, so now if we want to solve a standard form linear program, basically we want to solve an optimal solution. So instead of just looking at extreme points, we now will look at basic feasible solutions because they are defined with equations and variables. Because we know, given a solution, whether it is basic or not. To check it, it's very easy, right? If you want to check whether a point or a solution is extreme point, it can be very hard. But for basic solutions and basic feasible solutions, it's so easy. And then, obviously, we don't really want to enumerate all the basic feasible solutions because n choose m can be too large. So we want to search among them. And that means if I give you a solution, if I give you a basic feasible solution, you want to move to an adjacent basic feasible solution that is better. So let's define adjacent basis and adjacent basic feasible solutions. We say two bases are adjacent if exactly one of their variables is different. And then two basic feasible solutions are adjacent if their associated bases are adjacent. So again, let's just use a graph to get a rough idea. Here, this is our previous example. We have 4 extreme points or 4 basic feasible solutions. From a graph, easily you can say, okay, F and B are adjacent, B and A are adjacent, B and E are not adjacent, etc. Just following your simple intuition. If they share the same age, then they are adjacent in general. And then here, if you look at their basic basis, then for B and F, what do we see? For B and F, they share x3, and only one variable x1 and x4 are different. Okay, they share x3, and only one variable is different. For A and F, for example, for A and F, you can see non-variables are the same. They have 2 variables that are different. So that's why A and F are not adjacent. Okay, so that means if I want to move from one basis to another basis, all we need to do is to replace one variable by another variable. If I want to move from a basic feasible solution to another basic feasible solution, all we need to do is to, again, replace one variable. So that's the fundamental knowledge we need to have before we describe the simplex method. Basically, the idea is just, we know we only need to focus on basic feasible solutions. So I'm going to give you one, and then ask you to, in each iteration, move to an adjacent basic feasible solution that is better. Or that just means you should find an improving direction and move along it. If there is one, then you go. Otherwise, you have a basic solution that is optimal because around it, no solution is better. Okay? Okay, so that's the basic idea. Next, let's go into the details of algebras to talk about the simplex method. Thank you.